Hi everyone, my name is Özgüç Bertu Çapunaman and I'm pleased to be sharing my work with you today. The role of computers in design has been a topic of debate since early development efforts for computer-aided tools. Such attempts focused on liberating designers from the arduous tasks of design. This ambition heavily echoed Alberti's definition of skilled craftsmen to the idea of computational tools as perfect slaves. As the ambition to capture and codify the informal and often subjective design process as a whole failed, commercial efforts shifted the course of computer-aided design and manufacturing tools from creative endeavors to streamlined, representation-oriented tools. Although these tools are being adopted into the design process more than ever, the shortcomings and drawbacks of these systems often go unnoticed. Within the scope of this research, I point to two implementation inherent drawbacks of contemporary computer-aided design and manufacturing tools discussed in computer science, human-computer interaction, and computational design literature. The first one of these is the linear processing of information. Primarily, CAM tools heavily rely on pre-programming of toolpaths, which intrinsically inhibits users from exploring the design space. This, in turn, results in inflexibility to reflect and iterate on ideas quickly within the fabrication process, and increasingly excludes the human agent from the process altogether. Since the contemporary software packages are geared towards optimization and automation, the second limitation surfaces in the form of generic solutions offered by these tools. These algorithms often fail to capture nuances in materials and techniques and are overlooked by non-expert users that lack the means to navigate these complex computational systems. Lately, there has been growing interest in probing computer-aided tools to facilitate adaptive and interactive fabrication scenarios in fields like computational design, architecture, robotics, and human-computer interaction. Especially in the HCI community, one of the main areas of interest has been exploring alternative interaction interfaces ranging from augmented reality to capacitive touchscreens for digital fabrication purposes. In another approach, researchers have been looking into how establishing a sensory feedback loop between digital representation and physical artifact can enrich the fabrication process. Building upon the existing body of work, this research proposes an alternative interactive design fabrication workflow. Throughout this process, human and machine agents take on different roles with varying levels of contribution to the process. By investigating this turn-taking approach, this research aims to explore computer-aided systems not as sole algorithm executors, but instead as flexible facilitators of digital fabrication, capable of incorporating changes and adapting accordingly. This proposed workflow is mainly composed of a mechanical paste extruder, a laser stripe triangulation scanner, a real-time communication protocol, and Grasshopper and Python-based scripts. Before I share more in-depth information about the technical implementation, I would like to walk you through the workflow. The proposed design fabrication workflow starts with the initial geometric processing stage, where a slicing algorithm generates a series of toolpaths from the input geometry. Target planes generated by the slicer are then sent to the robotic arm layer by layer using a real-time communication protocol. The fabrication process is carried out until all layers are fabricated, or the user pauses anytime after a sufficient amount of material is deposited for the user to modify. Once the fabrication stage ends, the industrial robotic arm moves away from the fabrication environment for the user to safely manipulate the artifact by hand. Once satisfied with the geometric deformation, the user can initiate scanning of the artifact and subsequent digital reconstruction. Following the digital reconstruction, the geometric extrapolation algorithm generates a design hypothesis using the surface tangency of the reconstructed surface. Using the keypad inputs, the user can tune how compliant the extrapolation is with the surface continuity of the digital reconstruction and generates extrapolated toolpaths. Once the user confirms the geometry, the workflow transitions back into a fabrication stage and another cycle of fabrication is initiated. The exemplified cycle can be repeated indefinitely as long as the artifact is within the bounds of the scanner and the artifact is structurally stable. This proposed design fabrication workflow heavily relies on the subsystems to work synchronously, and the hardware and software implementations have been significant in pinpointing the limitations and potentials. One of these subsystems is the mechanical paste extruder. Based on an open source hardware project, this paste extruder was modified to accommodate fabrication with an industrial robotic arm. Additionally, a custom circuitry was implemented to allow increased control over material extrusion and to interface with other subsystems. The other subsystem that required hardware development was the laser stripe triangulation scanner. Aside from building and tuning the Cyclops 3D scanner kit, significant modifications were made to appropriate the hardware to the proposed workflow. For example, laser light sources were custom fitted with a 3D printed mounts to intentionally occlude the light to only shine on the side that is closer to the camera by lowering the light source. In addition to these hardware implementations, a custom geometric processing algorithm was implemented in Grasshopper for Rhinoceros environment. This algorithm utilizes point cloud data captured by the laser stripe triangulation scanner, first to reconstruct profile curves, and then to reconstruct and rebuild the fabricated artifact. Once the surface is rebuilt, the geometry is extrapolated following curvature tangency rules. Finally, the extrapolated geometry is sliced using a custom slicer, which makes it possible to have non-planar layers that adapt to the already fabricated artifact. During this geometric extrapolation, a parameter was implemented to allow users to explore curvature compliancy of the geometry and have greater control over how the algorithm is executed. As the last part of the development, a Python application was implemented to control and coordinate the data flow between different subsystems. In addition to custom geometric processing algorithm, Horus library was used to communicate with the laser stripe triangulation scanner, and Robot Ex Machina library was used to establish real-time communication with the industrial robotic arm. Although the setup is still primitive in implementation, the proposed design fabrication workflow provides an open-ended framework for creative inquirers. Here we see the results of the initial tests, primarily focused on testing reliable fabrication of the artifact. Even though experiment conducted in this stage of development failed due to implementation inherent problems, the experimental setup could successfully capture different topologies and perform geometric computation using the scan data. Once the implementation problems were solved, the proposed system was able to continue the fabrication of the artifact using updated geometry as a base to build upon. Here we can see how different geometric manipulations were processed between different cycles of the fabrication process. Although some discrepancies between the digital model and physical artifact are present, the proposed workflow was successful at capturing geometric intentions and using this information to extrapolate the geometry. Overall, the proposed design fabrication workflow presents an alternative approach to how design fabrication workflows can be extended beyond point-and-click interactions we are all accustomed to. The workflow achieves this by facilitating hands-on creative exploration and enabling design dialogue over matter. By enabling adaptive fabrication, by informing digital design and fabrication systems, and by probing computer-aided systems beyond representational operations as creative companions. Although early results with the proposed workflow are promising, some limitations shown here play an important role in the performance of the experimental setup. For example, while denser sampling of the artifact results in finer details during reconstruction, it quickly becomes a computationally expensive task. Additionally, the laser stripe scanner is prone to environmental lighting changes, and in many cases, a small amount of change in illumination can result in significant errors. Lastly, as much as the proposed workflow utilizes the malleability of clay, it can cause significant sagging in taller artifacts. Before I wrap up my presentation, I would like to acknowledge that this research has been completed at the Carnegie Mellon University School of Architecture and partially funded by Carnegie Mellon Graduate Small Project Help Research Grant. I would also like to thank the valuable advising committee, Joshua Bard, Daniel Cardozo-Yetch, and Minya Özkar for their support, insight, and expertise that greatly assisted this research. Thank you.